So, good morning, everyone. I'm Antonio Rizza, postdoc at the Space Rendezvous Lab at Stanford University. Today, we're going to talk about a novel position, navigation, and technology system to be used for absolute orbit determination. We'll start from having a look at the background, the motivation that pushed the need for this study. We'll then focus mainly on a methodology, and then we will validate the proposed approach with high-fidelity simulations that is based on a currently flying mission, the Starlink mission. And we will see some of the results and guidelines that we can draw from this analysis. So the current increase in space operations is leading to a few challenges from an operational perspective. We have a sustainability challenge, particularly in low Earth orbit, connected with a huge amount of space debris, resident space objects that populate the low Earth orbit environment. We have a security challenge because we need to develop strategies that are independent from GNSS to be robust against jamming and spoofing attacks. And we need to build navigation. Navigation pipeline that are able to achieve good performances also for deep space applications. So think about the gateway. Think about missions to Mars, to asteroids, and so on. That needs to rely on something that is not a GNSS system. So two main needs. We need to build an autonomous PNT pipeline that is, again, independent from GNSS. And we need to build something that is responsible to space situational awareness to preserve on-orbit assets. This work is based on angle-only navigation. Angle-only navigation means that we are using beacons to unresolved space objects. And we are using these beacons to retrieve the spacecraft positions, essentially. These beacons are detected by the image processing algorithm in the frames acquired by the camera, typically a star tracker on board. This technique is very powerful, but has some limitations, has some observability limitations, which essentially intuitively relates with the fact that whenever we are doing angles-only navigations, we are unable to resolve the range of the measure. The architecture proposed here, FALCON, consists in exploiting the fact that there are thousands of RSOs in Earth orbit, and these objects are tracked from ground. So we do have access to catalogs that store their positions. So the main idea is to compare these catalog informations with beacons, with line of sights computed on board to retrieve the observer positions and do absolute orbit determination. In particular, the pipeline that we propose consists in the following blocks that you can see here on the slides. We have a vision-based system. This is typically related with a star tracker camera or a high fidelity or a high resolution camera, for example, an image processing algorithm that detects the line of sights to the RSOs, a matching algorithm that associates this line of sights with the elements in the catalogs, and then a batch and a sequential orbit estimation pipeline. And bear in mind that this pipeline allows to do orbit determination starting from no prior on the observer positions. Let's dig into the details of the single components here. The image processing is a flight-proven image processing algorithm that was developed within the framework of the StarFox experiment and is currently flying on a Starlink mission. Essentially consists in performing centroiding on the objects that are seen in the camera field of view, using the pyramid algorithm to detect the known stars in the camera field of view and removing unknown stars by removing line of sights that are associated with the same inertial direction across consecutive observations. And essentially removing all of this from the camera field of view, whatever is left is an RSOs. Once these line of sights to the RSO are provided, the matching algorithm takes care of associating them with IDs corresponding to objects in the catalog. Now, I won't go too much into the details of how this is done, but the main idea is shown here on the right. If we have two different line of sights, what the algorithm does is pairing the line of sight that are detected in the camera field of view, and for each pair, finds the two objects catalog that lie on the plane that is defined by these two line of sights. This is done with no prior information on the observer position. So consider, for example, in this case, you have V1 and V2. And these two vectors, these two line of sights, define a family of planes that is shown by the letter pi on the figure. And the two objects that lie on that plane, C1 and C2, are the two RSOs that correspond to the observed line of sights. So this is done for every pair. And then all this information is combined and outliers are removed. And the bottom line effect of this is that we can generate a set of feasible matches that, starting from a data set of more than 20,000 RSOs, can reduce to a list of less than 5 possible feasible sets. This is still not a unique solution. So what we do is combining multiple observations, consecutive observations, to reduce this to a single valid match. Once the match is performed, we perform a batch orbit determination. We initialize the batch orbit determination in position by doing a triangulation of the line of sight for each frame, and in velocity by doing a finite difference between one observation and the other, between the estimated, between the triangulated positions of one observation and the other. And then we sequentially perform a batch estimation update until the step is reduced below a certain threshold. And once this process is completed, we also compute the covariance associated with this. Now, this estimation, this batch orbit determination that allows in few observations after the matching is performed, allows in few observations to initialize a sequential orbit determination pipeline that then allows for every new measurement to update the estimated solution. For the sequential orbit estimation pipeline, we use an uncentered Kalman filtering with a high fidelity dynamical model. The UKF uses a quasi-non-singular absolute orbital elements as state representation. The propagation step is performed by using a high fidelity dynamical model that takes into account for spherical harmonics up to order 10 and drag model. And the integration is done with a Runge-Kutta 4 with a 30 seconds time step. The correction step is instead performed by using a covariance modeling of the measurements that combines both assumed errors on the image processing and assumed error on the catalog objects. Now, this methodology is tested within a high-fidelity simulation framework. The simulation framework is the one of the NASA Starlink mission. This is a swarm of 4 spacecraft flying in low Earth orbit at an altitude of about 500 kilometers. You can see the relative configurations of the swarm in the top right of this slide. Among these, we pick SV3, the Starlink 3, as the observer to be used for this application. Why? Because this spacecraft is always observing in the flight direction, and as always, the other Starlink spacecraft in the field of view. So it seemed to be like a natural choice for running this test. This will have some consequences we will see in a second. Also note that the field of view is a very narrow field of view. It's a 5 by 6 degrees field of view. Then we pick a catalog objects of more than 21,000 objects retrieved from spacetrack.org. This consists in two line elements sets that are given at a reference epoch, RSO mean cross-sectional area, and the idea is to use this catalog for onboard computation. So how do we generate the ground truth for these simulations? We retrieve the initial conditions of the observer from GNSS data, from flight data. And then we propagate this in a high-fidelity simulation framework that takes into account for a higher fidelity gravity model, solar radiation pressure, and drag. And then we simulate uncertainties in the catalog by perturbing the two line elements at the initial epoch in a physically consistent way with an uncertainty that is sampled from a distribution that is elongated in the along track direction and is shrank in the radial cross-track direction. And then we also include uncertainties in the sensing by generating high fidelity synthetic images that can accurately reproduce the RSOs and the stars of the scene. Let's see some of the results. These results shows that we can get to a unique match from a lossy space condition. So from no information on the observer position, we can get to a unique match with just 3 observations that you can see here on the right. After 3 observations, we are able to retrieve exactly the IDs associated with the 3 objects that we are observing. And then once that is done, we proceed with feeding this in the navigation pipeline, and then we use the solution of the navigation pipeline to inform back the matching algorithm to facilitate the identification of the match. And the results shows that we have a success rate of finding the right match of 88%. The cases in which this doesn't happen is because there is a specific geometrical configuration, so we have alignment between the line of sights that lie on the same plane. So if you remember the figure I showed before, the match fails whenever we have 3 objects that lie on the same plane. And so it's within uncertainty, this is obviously a singularity point for the algorithm. Let's see some of the results from a navigation perspective. We see that we have good estimation capability for orbital shape, for semi-major axis and relative eccentricity axis, but we have large uncertainties. We have a drift that is observed in the along track direction. This is mainly due to 2 reasons. The first one is that the along track direction is also the boresight direction. So obviously, being an optical-based systems, we are unable to resolve the range. And the second point is that we are always observing the same spacecraft. Sometimes, as you can see from the figure, like we detect some RSOs that do not belong to the Starlink swarm, but most of the times we are observing the Starlink spacecraft. So we're observing spacecraft that are lying on the same orbits. And so the uncertainties on this spacecraft is correlated over time. And this is such that we obtain a drift in the estimation pipeline. So what happens if we don't use those measurements? What happens if we use other RSOs, observations of spacecraft that do not belong to the Starlink swarm? Well, performances are drastically improved in this case, even though convergence is lower, because of course now we have less measurements, less observations. So this suggests that we need a larger field of view. We need a camera with a high signal-to-noise ratio, and we need to observe RSOs that do not belong to the same, to the same orbital plane. Just to give you an idea, what happens if we then remove the uncertainty from the RSO? So now we have the same catalog for the ground truth and on board. Of course, results are much improved in this case, while we still have an offset, or at least we still have a large covariance in the along track direction due to the observability issue. So this suggests also something, this is an obvious result, but also suggests something important. It tells us that if we are able somehow to estimate the state of the RSO's objects and improve their knowledge, the knowledge on their state, we can actually improve the performance of the navigation pipeline that we are providing. We explored also different configurations. We tried to have a broader camera field of view with a higher acquisition frequency and with a higher sensitivity to the RSOs. And this is what we get. So in this case, we are actually same scenario, but we are observing in the negative flight direction. So we are not observing the Starlink spacecraft. We are observing other RSOs. We have a broader field of view. And as you can see, the performance in the navigations are much, much better. So to sum up, FALCON proposes a novel PNT solutions that is able to perform absolute orbit determination using only angles-only navigation. The methodology relies on combining catalog objects that are stored, a catalog is stored on board with the real line of sight detected by the image processing on board. The pipeline consists of 4 elements: image processing, catalog matching, batch orbit determinations, and sequential orbit determination pipeline. The methodology is tested within a high-fidelity simulation framework that takes into account for uncertainties in dynamics, catalog, and sensing, and shows promising performance. The catalog matching is able to converge in only 3 iterations with no information on your observer positions. The batch orbit determination is able to initialize the SOD pipeline with after 3 consecutive observations. And the sequential orbit determination pipeline is able to provide, with the right choice of beacons, an accuracy that is on the order of 2 kilometers in the along track direction and 200 meters in the radial direction. We also explored improving the designs with larger field of view and more sensitive cameras, and we showed a drastic improvement of performance. So the next step after this is moving towards the estimation, the SSA applications of estimating the state of the aerosols, to both for an SSA purpose and to improve the navigation performances. And with that, I thank you for your attention. If you have any questions, I'll be happy to answer.